This video covers Griffiths E&M, section 7.2, Faraday's Law. So far, we have essentially seen all of the Maxwell's equations in some form. We have, in differential form, that the divergence of the electric field is related to the charges. The curl of the electric field is equal to 0. The divergence of the magnetic field is equal to 0. And the curl of the magnetic field is equal to something related to the current. Okay, this was Ampere's law. This was Gauss's law. All right, and today we're going to talk about Faraday's law, which is an extension of this bottom expression here. Okay, so we're going to talk about EMF. We refer to EMF like we talked about in previous videos. We have some region of space. Let's say that region of space has a magnetic field that points into the page. I have a wire connected to some load. Put the load there. If I go ahead and move that wire with some speed v, and we know that we generate a current. Okay. Right. So the EMF from the moving charges generates a current. Okay. So there's also the scenario where I have the same region of space creating some magnetic field, and I have the same loop, but instead of moving the loop, I move the magnet, move that region of space that's creating that magnetic field, and we would still find that there's a current that flows through our wire. Okay, maybe that's not such a problem, right? So these charges still have some relative speed, right? From the only difference in these two pictures is where you're putting your reference frame. Okay, there's still some relative speed between the magnetic field region and the wire. Okay. However, what if I take the same region of space same magnetic field, I then keep the same wire and I don't move the wire or the magnetic field at all. If I don't move the wire or the magnetic field, I don't have any magnetic force that's generating EMF. Okay, but what Faraday says is, well, what if you have that magnetic field change in time? And that changing magnetic field is still able to generate a current. It still generates a current, but it's not from the magnetic field. Okay, so what can force a stationary charge to move? Right? I have this expression for my magnetic force, which is related to the speeds of those charged particles. If the speed is 0, then the magnetic force is 0. Well, the thing that generates a force on a stationary particle is an electric field. Okay, so there's some sort of connection between this changing magnetic field and the existence of an electric field. That's what Faraday did. Faraday said, all right, well, now the curl of the electric field is not necessarily 0. It is related to the magnetic field if it changes in time. Okay, so the first thing I see when I see this expression is, well, in electrodynamics, where things are changing in time, I no longer have this expression that the electric field is curlless. And if the electric field is not curlless, then I can't simply write that the electric field is negative the gradient of some scalar potential. Okay. So what is an equivalent expression for this? Okay, I'll take my curl of my electric field minus the time rate change of my magnetic field. I'm going to write the magnetic field in terms of my curl of my vector potential. I can write all of this as the curl of some quantity of the electric field and the time rate change of that vector potential. That is equal to 0. So now this quantity is equal to the negative gradient of my scalar potential. Or equivalently, my electric field is what it used to be, but modified by some changing magnetic vector potential.